We've now completed our study of descriptive statistics, where we talked about collecting data and then describing that data in a variety of ways, such as computing the mean, median, and mode, standard deviation, drawing a frequency polygon or a histogram, so on and so forth. If the data we've collected and described is the entire population's worth of data, then we're essentially done. However, people often want to know information about much larger population sizes where we can't get all the data. So instead, we have to settle for a subset of the larger population known as a sample. Once we start doing computations with respect to the sample, we want to know how likely are our computations how likely are they a good representation of the actual population parameters? This now requires the concept of probability. In order to make predictions about a population from sample data, we need to be able to say with what likelihood or what chance or what probability our sample computations, known as statistics, represent the larger population. So we are now going to cross the probability bridge that takes us from descriptive statistics to the second part of statistics known as inferential statistics. Let's start our study of probability with an example. So here's the probability experiment, or the game in this case. You flip 3 coins. What's the likelihood that exactly 2 of them are tails? So just to make sure everybody's clear, likelihood, chance, and probability are all synonyms. They're all representing the probability of something occurring. So you want to know if you flip 3 coins, that's our probability experiment, what's the likelihood exactly 2 of them are tails? Right? So, for example, you could flip the coin and get, and I'll write this down here, tails and then a heads and then a tails. Or you could flip the coin and get a heads and a heads and then a tails. Or you could get a heads and a heads and a heads. To understand what could possibly happen in an experiment, we need to know what the sample space is. So the sample space S, we use the capital letter S to represent the sample space, is the set of all possible outcomes of a probability experiment. Each one of these is an outcome of this probability experiment. We need to know what all of them are. However, going about it haphazardly this way is a bit dangerous. You might end up repeating something or missing something. We're going to draw a graphic called a tree diagram that shows us the entire sample space. With the tree diagram, it's nice and orderly and organized so we can be sure that we've not missed any outcomes or repeated any. So I'm just going to draw up here a little start box. And we're going to write down what could happen on each flip based on what happened on the previous flip. So here's flip 1. On flip 1, you could either get a heads or a tails. We'll use H to represent heads, T to represent tails. Now we're going to now look at flip 2, but we're not going to look at flip 2 without looking at flip 1 first. So suppose in flip 1 you got a heads. Then in flip 2, you could get a heads or a tails. The second flip is completely independent of the first flip. You could get a tails on the first flip. Then from there, you could get a heads or tails. Then we have flip 3. And with flip 3, we are going to consider the previous 2 flips. So with flip 1 and flip 2, you could get a heads and a heads. Then from there, you could get a heads or a tails. There's no reason that you would have to get heads again. There's still a 50% chance of getting heads and 50% chance of getting a tails. Then you could also get a heads and a tails on the first 2 flips. Then from there, you could get a heads or tails on flip 3. And same idea over here. This now accurately represents the entire sample space of this experiment. Each path from the top to the bottom is an outcome of the experiment. So this first one here is heads, 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 and we're going to list the sample space now. S is equal to heads, heads, heads. That's one of them, and we separate the outcomes with commas. This is right here, this is set notation. The next outcome in the tree diagram is heads, heads, tails. The next outcome in the tree diagram is heads, tails, heads. The next one is heads, tails, tails. The next one is tails, heads, heads. We've got tails, heads, tails. tails, tails, heads, and tails, tails, tails. We've now created the entire sample space for this probability experiment, and I'm confident that we've not repeated anything or missed anything because we went through it very systematically by using this tree diagram. Once we know what the sample space is, we then need to focus on a subset of the sample space known as an event space. The event space E is a desired subset of the sample space. And what we desire in this particular case is we want to know what's the likelihood of getting exactly 2 of them are tails. So this is our event, getting exactly 2 tails. So let's go through the sample space and find out which outcomes satisfy the condition. If you look at the first one, heads, 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 does not have exactly 2 tails. Heads, heads, tails, the next one does not have exactly 2 tails. Heads, tails, heads does not have exactly 2 tails. Heads, tails, tails does have exactly 2 tails. So we have, this is one of the elements of our sample, or of our event space. The next one does not have exactly 2 tails. This one has exactly 2 tails. This one has exactly 2 tails. This one does not. It's got 3 tails. It's got to be exactly 2 tails according to the event E up here. So our event space here is equal to heads, tails, 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 heads, tails, and tails, tails, heads. There is no order in these sets, so you could put them in a different order. It doesn't matter. It would mean the same thing. Our sample space is this. Our event space is this. We can now answer what's the likelihood or the probability of getting exactly 2 tails. Well, how many things could possibly happen? Well, that's what the sample space represents. It's all the possibilities. So if you count this up, there's a total of 8 possibilities. And then how many of those 8 possibilities are our desired outcomes? Well, this one, and this one, which is a total of 3. So there's a 3 in 8 chance, or a 3/8 chance, that you will get exactly 2 tails when you flip a coin 3 times. This is our probability. And we need to formalize this idea. But before we do that, make sure you realize probabilities can be written as fractions, decimals, or percents. Let's first formally define the definition of probability, or specifically theoretical probability, which is the type of problem we were just doing, and also see the notation that goes along with it. Well, if you can recall from the past, function notations such as f of x equals x plus 2, this is read as f of x. F is the name of the function, and x is the input of the function. This is function notation right here. And we read this as P of E. P of E, where E is the event, and P represents the probability of the event occurring. So P of E means the probability of event E occurring. On the previous screen, we found that the probability of the event E occurring where E was getting exactly 2 tails was 3/8. This 8 right here was the total number of outcomes in the sample space. Total number of outcomes in the sample space. The formal notation for that idea is precisely this. So that those absolute value bars around the S, that means the size of the sample space. So size of sample space. And then the 3 up here was the size of the event space. So total number of outcomes in the event space. So this notation right here with the absolute value bars around E represents the size of the event space. So theoretical probability, which is whenever you have equally likely possible outcomes, is the size of the event space divided by the size of the sample space. That's our formal definition of theoretical probability. Notice here we also have another probability defined. It says empirical probability. Empirical probability is probability based on collected data. So based on collected data. You will see an example on the next screen of empirical probability. It's pretty straightforward, but this notation right here is exactly what you know from the unit 1. F is the frequency, and n, lowercase n, is the sample size. We'll see an example of that in a little bit. So we've got theoretical probability defined, we've got empirical probability defined, and then there's two important other concepts here. This says that no matter what event you're talking about in any probability experiment, the probability of E occurring is always between 0 and 1. It never goes below 0 and it never goes above 1. Or equivalently, if you're thinking about this as percentages, the probability of E occurring, no matter what experiment you're talking about or what event, it's never less than 0% and it's never more than 100%. So 110% makes no sense in the probability setting, where it might in a business application. For example, you could make 110% profits from the previous year. Going over 100% or below 0% makes no sense in probability theory. The reason is the event space is a subset of the sample space. So the size of the event space is never larger than the size of the sample space. So it never goes above 100%. Same idea here with the empirical probability. Also, it would never go below 0 because it would never be negative. Your sizes can never be negative. And you see there's one more probability fact here involving the complement of an event E. So the notation for the complement of an event E is E prime. That's read as E prime, where you've got the little tick mark here in the superscript position on the E. The complement of an event is everything else in the sample space that's not in the event E. So for example, if this is your entire sample space and all of these outcomes are in your event E, then the complement is everything else out here. It's all the other possible outcomes. So the complement, for example, of getting exactly 2 heads, or sorry, 2 tails was on the previous screen. The complement of getting exactly 2 tails when you flip a coin 3 times is precisely not getting exactly 2. So getting 0 tails, getting 1 tails, or getting 3 tails. So not exactly 2 tails. And there's a very nice relationship between the probability of an event and the probability of its complement. In general, the probability of an event plus the probability of its complement always adds up to the total of 1. Or written differently, the probability of E prime is equal to 1 minus P of E. This is the same thing as this, just in this one, the P of E prime is isolated. If you subtracted P of E from both sides here, you get exactly this. So for example, if I wanted to know the probability of not exactly 2 tails, according to this formula, that's 1 minus the probability of getting exactly 2 tails. So 1 minus the probability of getting exactly 2 tails, which we saw was 3/8. 1 minus 3/8, of course, 1 is 8/8. So if you take 3 away from 8, you've got a total of 5/8 left. These are the definitions of our 2 types of probability, and these are 2 very important facts about probability that apply to both theoretical and empirical probability.